Alrighty, Newton's laws of motion. There are 3 of them. Let's take a quick look, hey? The first law is known as the law of inertia. It states that an object remains in constant motion unless acted on by an outside resultant force. So basically, we have constant motion. That's what this first law is all about, is that motion will be constant unless we have an outside resultant force or a net force or an unbalanced force. Resultant, net, unbalanced, same. They're all applying to the same idea that we have a force that is not cancelled out by any other forces, right? So we've got constant motion unless we have a net force acting. Now the second law says, well, okay, what if we did have that net force acting? Well, without the net force, we've got constant motion. So with some sort of net or resultant force, our motion is not going to be constant. And motion that is not constant is called acceleration. So if we have a force acting on a mass, that mass is going to accelerate. F equals ma. Newton's second law of motion is often just sort of summed up as F equals ma. Now, another couple of points to this one though. One is that the acceleration is in the same direction as the force, and another one that the size of the acceleration is directly proportional to the size of the force. So a bigger force, you get a bigger acceleration. Okay, there is another law. The third law of motion is essentially the fact that forces come in pairs. For every action force, there is an equal and opposite reaction force. Alright, so there is a very quick sum up of Newton's 3 laws of motion. Let's just go over a few questions involving these Newton's laws and see how they apply. Alright, the first one is about circular motion. So we have the sun. There it is, and we've got Earth. Here we go. Now, according to Newton's first law of motion, that Earth is trying to go in a straight line. But of course it's not. It's going around and around the sun. Why is that? Well, there is a net force acting. That net force is, of course, the force of gravity. So the Earth is attracted by gravity towards the sun. The sun is also attracted towards the Earth, of course, by gravity, but the sun is much more massive. It has much more gravity than the Earth does, so we generally just say the Earth is attracted towards the sun. But really, gravity is the force of attraction of 2 masses towards each other. Yeah. So anyway, the Earth is trying to go in a straight line, but it can't because that net force, the force of gravity, that unbalanced force or the resultant force, is changing its motion. Now, change of motion, acceleration, could be speeding up, could be slowing down, or could be changing direction. And that's what we have in this case. The Earth changes direction. But then there's still gravity, and the Earth changes direction. But then there's still gravity, and the Earth changes direction. Then there's still gravity, and guess what? The Earth changes direction. So what do we end up with? The Earth going around and around the sun. We end up with circular motion. Now, if gravity were stronger, the Earth would spiral into the sun. If gravity were weaker, the Earth would spiral outwards away from the sun and eventually be gone. But luckily for us, there's a nice little balance between the Earth's forward motion and gravity towards the sun, so it just keeps going around and around quite nicely. Next question. Car's traveling along, the engine stops, maybe ran out of petrol, who knows, not really important, but the engine stops and the car slows down and stops. Which of the following could explain this? Well, the car doesn't run out of force, the car didn't have force. I guess the motor was supplying force initially, and then the motor stopped, so the motor stopped supplying force, but you can't say the car ran out of force. The car just stopped naturally, but it can't be that one, because according to Newton's first law, things don't just stop naturally. Things in motion stay in the same motion. Gravity is holding the car down on the road, so it can't be that one, and I guess that leaves us with friction, which is of course the answer. According to Newton's first law, that car is an object in motion and will stay an object in motion, unless acted on by a different resultant force, right? And that resultant force is friction. Friction is a force that opposes motion. So even though the inertia of the car tries to keep it going, friction says, hey, no you don't, slow down and stop. Okie dokie, next one. Now this has got a word that we need to be careful of. Weigh. It's not the same as weight, right? When we say, what do you weigh? Like, hey, I jumped on the scales and I weighed 58 kilograms. Or what do you weigh? Oh, I weigh 68 kilograms. When we say weigh, in general terminology, we're meaning the mass. So here we have a 1 kilogram mass. What would it weigh on the moon if the pull of gravity is 1/6 of what it is on Earth? Well, it would still weigh 1 kilogram because its mass would still be 1 kilogram. Now, if the word has a T on the end, weight, well, now we're talking a force measured in newtons. All right, but as this question is written, it just says, what would it weigh? It would weigh 1 kilogram. That refers to how much mass there is. But there is a question coming up which deals more with weight. So remember, mass is just how much matter there is in an object. Weight is the force of gravity acting on that mass. Okay, cool. So we'll deal with weight at a future question. All right, 2 tins. A is full of wet sand and B is empty. So essentially, A is heavy, B is not. Which tin is harder to push? Hopefully you'll agree it's A. Why is it A? Because it has a larger mass, and because it has a larger mass, that means it has more inertia, a greater inertia. Now, what is inertia? Let's just scribble this down. Inertia is the resistance to change motion. Resistance to change motion. Triangle is just the Greek letter delta, and that stands for change. So if you see a triangle like that, that's just shorthand for change. So inertia is the resistance to change of motion. So tin A, it has more mass, therefore it has more inertia, therefore it's more resistant to a change of its motion. So it's harder to push initially because it was just hanging there and you're trying to change its motion by pushing it. But it's harder to change that motion, so it's harder to push. But it's the same from the other side of the coin as well. When it's already swinging and you want to stop it, it still has a larger mass, and so it still has more inertia, so it is still harder to change its motion. Right? It has more resistance to the change of motion, the change being you trying to slow it down and stop it. So which one's harder to stop? Also A. All right, this one's a good little party trick. Knock the hoop out to the side, and what happens to the sugar cubes? Well, they stay there momentarily, and then they fall down into the bottle. What's going on? Well, it's Newton's first law of motion, and it's Newton's second law of motion. Let's start with the first law. The first law says that objects will remain in constant motion unless acted on by outside resultant force, blah, blah, blah. Yep, we know that one. Well, the force is only acting on the hoop. So only the hoop gets accelerated away, according to Newton's second law, that when that force applies to a mass, the mass accelerates in the same direction. So if the ruler knocks the hoop, in this case to the right, and the hoop is going to fly off towards the right. Now, the sugar cubes, which were supported by the hoop, they were objects at rest. And according to Newton's first law, they stay objects at rest. So the hoop's not there, it's over here. And then the sugar cubes have stayed where they are, but now they're not supported anymore. They're just sort of sitting in the air very momentarily, and then gravity does its thing and pulls them down into the bottle. Now, of course, the hoop will need to be knocked quickly. If you just sort of slowly start to push the hoop, well, friction is a thing. With Newton's laws of motion, friction doesn't really feature, but we don't live in a world without friction, right? Friction is everywhere. So if you just slowly push the hoop off to the side, the sugar cubes are going to experience the force of friction and be dragged along with the hoop, and so they won't actually fall straight down into the bottle. So you give the hoop a nice quick whack off to the side, and then the sugar cubes down into the bottle. State Newton's third law of motion. Well, remember, this is the pairs one. So essentially, forces act in pairs. For every action force, there is an equal but opposite reaction force. That's Newton's third law of motion. Now, this next question actually also is dealing with the pairs of forces. Okay, so we have the gravitational force pulling the block of wood down. We have the supporting force of the table pushing the block of wood back up. Equal but opposite forces. This is Newton's third law of motion. So the gravity is trying to pull the block down. If gravity were stronger, the gravitational force was stronger than the supporting force, the block of wood would be crashing down through the table. If the supporting force were stronger, then the block of wood would be bouncing back up into the air. But because the forces are equal but opposite, the block of wood just sort of sits there on the table. Alrighty, another fun demo here with this one. So you've got a stack of coins and a ruler, and you swipe the ruler along the surface of the desk, so down near the bottom coin, but you swipe it across to the side. Now this is Newton's second law. F equals ma. You are going to apply a force on that bottom coin, and the bottom coin is going to fly off to the side in the same direction as the force was applied, and a bigger force will mean more acceleration, so it'll really shoot off to the side. Then we have the first law on the rest of the coins because they were objects at rest, so they stay there. But then you knock out the bottom coin, so they're not supported by that bottom coin, so gravity does its thing and pulls them down. Okay, so our stack is now one coin shorter. This works quite nicely if you get a ruler that is just the right thickness, essentially the same thickness as one of the coins. And what you can do is slide the ruler back and forth, side to side, side to side, side to side, flicking a coin off to the left, then off to the right, then off to the left, then off to the right, until you have exhausted your stack of coins. But there you go, nice little trick involving first the second law and then the first law of motion. All right, cars moving along, horizontal road, constant velocity, blah, 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 blah. Okay, so essentially vector x is the force from the motor, and vector y is the force of anything trying to stop the motion, okay, like friction and air resistance, etc. So the question really is x greater than y, or is y greater than x, or are they the same size force, or none of the above? Well, it's not none of the above, it is one of the above, so let's get rid of d. Right, what's actually going on? Well, if x were greater than y, the car would be accelerating towards the right. If y were greater than x, the car would be accelerating towards the left. Now, I didn't say moving towards the left, I said accelerating towards the left. The car could quite well be going towards the right, okay, moving towards the right, but acceleration towards the left just means that the car is slowing down, right? However, what we have is constant velocity. Now, according to Newton's first law of motion, how do we have constant motion? When there is no net force, there's no resultant force. And how do we have no resultant force when these forces are the same size and they cancel out? So the answer is C. X is equal to y. Now note that all the forces have cancelled out doesn't mean that the car isn't moving. Okay, it is moving at a constant velocity. The forces being all cancelled out simply means that there's no change of velocity. Hence the question said constant velocity. Moving on, we have a peg that has been opened and held open with some string and a small and large marble placed either side. You cut the string, what happens? Well, the large marble flies off this direction and the small marble flies off this direction. Which one goes furthest? Well, the small one. We're looking at F equals ma, Newton's second law of motion. The force applied to each marble is actually the same because it's supplied from the peg, which is just doing its nice little closing business that pegs like to do. So the force is constant. But for a smaller mass, if the force is constant, you're going to get a larger acceleration, which will translate to going further. Okay, so we can test this idea just with some random numbers. Let's look at 24 is equal to, what should we go, 6 times 4. There we go. 6 fours are 24. Now, if we want to keep this answer the same, we want the answer to be 24, but if we lower the 6 and call it a 3 instead, we're going to have to up the 4 and make that an 8, right? So what we did was we lowered the mass and we had to up the acceleration in this case, right? Conversely, if on the other hand we up the mass because we're talking about the large marble now, well, we're going to have to down the acceleration. So it's going to have lower acceleration, which will translate as it won't go as far. So there we go. The small marble will travel the furthest, and this is all to do with Newton's second law of motion. All right, this next one here is just dealing with resultant forces, working out the net force. Okay, well, we can work out the net forces by adding the forces together. So for A, we have 4 newtons of force this way to the right, and then we also have 4 newtons of force this way to the right, and we started here and we went to here, and that is our resultant force, 8 newtons to the right. So we just add them. When we have arrows for forces like this, we can just add them top to tail. For B, Well, we've got 3 newtons this way, we've got 3 newtons this way, and those 3 newtons cancel out those 3 newtons, and what resultant force do we have left? None. There is no resultant force, right? Or a resultant force of 0 newtons, which is no force. So there we go. There will be no change of motion to B. Doesn't mean that B is not moving. If B were already moving, it would just keep that constant motion, right? According to Newton's first law. So it could be moving, it could be stationary, we don't know. All we can say is there is no resultant force, so its motion won't change. Now, C, we had 8 newtons this way, 3 newtons this way. Those 3 newtons will cancel out 3 of the 8 and still leave us with 5 newtons of force to the right, all right, as our resultant force. Okay, next question. Now, this is actually the question I alluded to earlier, that there would be a question coming up. Another one with the whole weight kind of situation, yeah? So this time we're looking at weight, not weigh. So we have a mass of 60 kilograms. Lovely. What is the astronaut's mass on the moon? You'll note I'm jumping straight to the last one because that's an easy straight up 60 kilograms. The mass doesn't change depending on where you are. Okay, mass is how much matter goes in to make up an object. So if you have a mass of 60 kilograms on Earth and then you teleported to the moon, your mass is still 60 kilograms. Now, I say teleported because if, for instance, you were launched on the Saturn V rocket, you were part of the Apollo lunar missions, that actually took a few days to get to the moon. And over that time, you would eat and your mass would go up, and you would go to the toilet and your mass would go down. So, you know, there are things that can change the mass, sure. But if you did it straight away, like maybe you teleported, the mass doesn't change. So far, so good. Now, what is the astronaut's weight on Earth? Well, remember, force equals mass times acceleration. That's Newton's second law of motion, isn't it? Well, weight is a force. So there's your force. We're talking about a mass, and we know the acceleration on Earth. It's the acceleration due to gravity. Now that's about 10. Now really it's more 9.81, but for a question like this, let's just do it real quick with simple numbers and we'll call it 10. We'll round to 10. So the weight of the astronaut on Earth is now simply 60 kilograms times 10 newtons per kilogram, and that comes out with a weight force of 600 newtons. You'll note weight is a force measured therefore in newtons. So she has a mass of 60 kilograms and a weight of 600 newtons. Like I say, her weight would actually be a bit less than this because gravity on Earth isn't 10, it's 9.81, but 10 makes for nice numbers. Now, she teleports to the moon. What is her weight now? Well, remember from that previous question, don't know that we actually read all this into the question. I think we went straight to the answer, 1 kilogram. Because the mass didn't change. But the question did state that the gravity on the moon is 1/6 of what it is on Earth. It's 6 times less. So that means the weight on the moon is going to be 1/6 of her weight. Okay, so her weight on the moon is 100 newtons. And like I said, it would be a bit less than that, you know, if we use 9.81. But let's just use 10 for gravity, just to make the question easy in this case, because I can't be bothered reaching for a calculator. What does Newton's first law of motion state? Oh goodness, I don't really want to write it down because I can't be bothered. Constant motion unless a resultant or net or unbalanced force. There we go. If you wanted to spell out the whole thing, you would say something like an object will remain in constant motion unless acted on by an outside resultant force. Oh, the old tablecloth trick. It's not magic, is it? It's just science. Should the person pull the tablecloth quickly or slowly? Let's go quickly. Firstly, because we can see in the diagram there are little speed marks there, so she must have pulled that tablecloth really quickly, yeah? Secondly, if they had pulled the tablecloth slowly, the bowl and the 2 cups and the spoon would also fall onto the floor and maybe break because of friction between the objects and the tablecloth. When you pull the tablecloth really quickly, you only apply the force on the tablecloth. Newton's first law of motion says that the bowl and cups and stuff, objects at rest, they will stay at rest. And much like the hoop and sugar cubes and the ruler knocking the coins out, once the tablecloth is moved very quickly, the other objects being at rest will not be supported by the tablecloth. They will now fall down. The sugar cubes into the bottle, the coins down onto the table. In this case, the bowl and cups, they just fall down onto the table as well. once the tablecloth has been removed. But yeah, move it quickly. There we go. And the physics of this trick are explained by the first law of motion, that the objects on the tablecloth were at rest, and so they will stay at rest. And yeah, there we go. Oh, actually, I guess, and also the second law, because the force was applied only on the tablecloth as our mass, so the tablecloth accelerated out to the side. The force wasn't applied to the other objects, so they stay there. Cool. Moving on. Okay, here's a good question. Air resistance time. This is terminal velocity, this question. So you'll note when the person jumped out of the plane, they had 0 speed meters per second. Now, that's vertical speed. Their vertical velocity was 0, okay? Because the plane was flying along horizontally. They did have some horizontal speed, of course, but we're looking at the vertical speed here. So they didn't have any vertical speed, but then they're no longer attached to the plane anymore, so they start accelerating towards the ground. So they get faster, faster, faster. But actually, you'll note that that acceleration sort of tails off, tails off, tails off, and then they end up going at a constant speed. Well, that's what we call terminal velocity, isn't it? It's that section between B and C where the person is actually falling at a constant speed. So what is his speed at point A? Let's go through these questions. Right. Well, that's when they've just jumped out of the plane for some who knows what reason. Some people like to do crazy stuff like jumping out of a perfectly good plane. But anyway, their speed is 0. We're talking their vertical speed is 0. So there we go, 0 meters per second. What is the speed at point B? Well, that would be 50 meters per second, just reading these straight off the graph. So that's, of course, the vertical speed, 50 meters per second. How long does it take to accelerate to terminal velocity? Well, if we go like this, to me, I'd say it's a bit less than 20 seconds. I'm going to call that about 18 seconds. What happens to the speed when the parachute opens? Well, you'll note it very, very quickly drops off. Right, so they open the parachute at C, and the speed was about 50, and it drops to about 10. Now that happened in about maybe 5 seconds, looking at the graph. So the speed dropped off really, really quickly. Okay, opening the parachute makes for a very large increase in surface area, and the more surface area, the greater air resistance, and the more air resistance, the lower the speed. Okay, that's why we use parachutes. They increase the surface area, which means more air resistance, and they slow us right the heck down. So what happens to the speed when the parachute opens? It drops off really quickly. Drops off quickly. And this is a good thing, because then you won't go splat into the ground, so we like that. How long does it take to decelerate to terminal velocity? Well, to look at the graph, I reckon maybe 5 seconds. Now, to decelerate to terminal velocity, they were already at terminal velocity. What the heck? Yeah, well, one was without the parachute and one was with the parachute. Okay, so terminal velocity just means that the speed is no longer changing. If you didn't have a parachute and you pulled your arms into your body and you shaped yourself like a bullet, you'll have an even faster terminal velocity. You'll speed up, but eventually you will stop speeding up and you'll reach a terminal velocity again. So terminal velocity just means your speed isn't changing. So there we go. That question done. Moving on. When a tennis player hits a tennis ball, what forces are acting on the ball? Right, so a lot of people might like to say C, but a lot of people would, of course, be wrong. The force of the hit is no longer acting on the ball. As soon as the tennis ball leaves the tennis racket, that force is not applied anymore. So the only force is the force of gravity. There's also air resistance, I guess going back the other way, but that's not one of our options. Okay. Now, I guess you could argue, well, air resistance technically is the force of friction as the ball is pushing its way through the air molecules. There's friction there. Yeah, no, let's not get all nitty gritty. It's the force of gravity is still acting. If this question, on the other hand, had said, as the tennis ball flies over the net, what forces are driving that tennis ball over the net? Then we would go for D, no forces, because it was just an object in motion. And according to Newton's first law, it stays an object in motion, right? But this question, as it stands, gravity is always acting. So there we go. We've always got the gravity. Next question. Oh, this is very similar to a question a couple ago. So we've got skydiver jumps out of a plane. Silly skydiver, stay on the plane, it'll land. But anyway, some people like to go skydiving, and we, by the looks of things, have to arrange the diagrams in the correct order. Okay, cool. Let's do that. Correct order. Right. Well, first I'm going to say C. The person is falling down. So correct order would be C. So this one is first. Cool. And then, oh, he's standing on the ground, so I reckon this one is going to be fifth. The last one has to be, they've landed on the ground. Now, A and E both have the parachute open. D doesn't. So D must be second. Okay, because first the person had just jumped out of the plane, and we have this force accelerating towards the ground, the force of 700 newtons. Now, as soon as they start building up that vertical speed going down, then the air resistance is going to be building up, building up, building up, until eventually they're going so fast that the air resistance has built up so that it's the same as the gravitational weight force pulling them down. So that's our D. Okay, so the forces are now equal but opposite, and we have reached terminal velocity. Okay, and then they open the parachute, which is going to be this one. Now, why this one? Because the force of air resistance is more than the weight force pulling the person down. Okay, when you open your parachute, there's a very sudden increase in surface area, so that's a very sudden increase in air resistance, and that will very quickly slow you down until eventually, as you go slower and slower, the air resistance will come down and down and down until, that's now diagram A, so the fourth one, until the force of air resistance is once again the same as the gravitational force pulling you down. Okay, and then, like I said, fifth one, the person is on the ground. Okay, cool. So there's our order. What do we have to do now? Drawing label, explanation. The parachute has opened, and the two forces, friction and weight, now become equal again. Well, that looks like drawing label A, and that was the fourth one. There's only one force on the skydiver. That's immediately as they jump out of the plane. That force is gravity. So that's C, was number one. The resultant force, air resistance, is now upwards, making them slow down. Well, that must be E, when the air resistance is more than the weight force down, right? The resultant force is now up. So they accelerate upwards. But the person was already moving down, so generally we say they slow down. But because they were moving down towards the ground, but getting slower and slower, that is actually the same as accelerating upwards. So that was number three. As they free fall, the forces, friction and weight become equal, stops accelerating, falls at a constant speed, which of course we call terminal velocity. Well, that was D before they opened the parachute. That was the second one. And then of course on the ground is the last one. Hey, go back. There we go. What am I doing? B. There we go. Cool. Done. And now this question that you got a quick early glance at. So what we're doing here is we pull the trolley and the ball rolls to the back. Or does it? Well, no, it doesn't, but it looks like it does, right? So if the trolley is pulled forward, forward towards the right in this diagram, the ball appears to roll back and hit the back of the trolley. What's actually happening? Newton's first law is actually happening. Newton's first law says that that ball is an object at rest, and it will stay an object at rest unless acted on by an outside resultant force. Well, guess what? You're pulling on the trolley. You're not pulling on the ball. So there is no resultant force acting on the ball. It stays where it is. But the trolley doesn't, because you're applying a force to that object, and that will accelerate, according to Newton's second law, in the same direction of the force. So you pull the trolley to the right, the trolley will move to the right. So it's not that the ball rolls to the back of the trolley. The ball stays where it is, but the trolley is moving underneath the ball until eventually the back of the trolley catches up to the ball, or meets with the ball. And so wait, back of trolley, ball, oh, the ball rolled to the back. Yeah, but actually it didn't, did it? The ball stayed where it was. The trolley moved under the ball. So there we go, Newton's first law of motion. It's a similar idea when you're on a bus, isn't it? So here's a bus, and here's you. Now the bus is moving this way and you are moving this way as well. Yay, grand. Except then the bus decides to turn the corner. And what happens when the bus turns to the right? You fall to the left, don't you? You fall onto the people sitting on that seat, because you were standing up, by the way. But no, you didn't actually fall. You kept going in a straight line. What's changed is now the bus is now going this way because it turned to the right. But you're not bolted to the bus. You were your own object moving in a straight line according to Newton's first law. So where do you move towards? The people on the left side of the bus. So it's like you fell over onto the people on the side, but actually you kept going straight ahead. It was the silly bus which turned out from under you. All right, cool. So it's that sort of idea. Okie dokie, another one. Use the words below to complete the table. Yeah, sure. Speed in a particular direction. Well, that's what we call velocity. The unit we measure forces is, of course, the Newton. An object's resistance to change in motion, well, we said earlier that's inertia. It is the resistance to change in motion. The rate of change of velocity. Okay, change of velocity, that's acceleration. There we go. And by process of elimination, the force of gravity pulling an object towards the Earth, that is, of course, weight, which we also looked at in a previous question. All right, moving on. You're standing on a bus. What happened? Oh, actually, let's just go back. There we go. And we've kind of already answered this question. We already talked about a bus. Go figure. Okay, so what happens when the bus starts moving? You appear to fall back, but remember, you were an object at rest. It's the bus that starts moving out from under you, bringing the back of the bus closer towards you. But that seems like you falling towards the back, doesn't it? When the bus stops moving, again, you're not bolted to the bus. The bus might stop, but you're an object in motion. You keep going. All right. This is why we wear seatbelts, isn't it? Because if the vehicle stops suddenly, well, you were an object in motion. You keep going, and that's called going out through the windscreen, right? And we don't like that. So we wear our seatbelt to stop us from doing that. When the bus turns to the left, you appear to fall onto the people to the right of you, but actually you were going in a straight line, and the right side of the bus just came closer to you, as like I drew in that earlier diagram. And which of Newton's laws? Well, it's the first law of motion. Okay, grand. Moving on. If you pushed both supermarket trolleys with the same force, which would be the easiest to get going and why? Well, just to make sure you can see, this one is full. Trolley B is full of groceries and trolley A is rather empty. Okay, so which would be easiest to get going? Simple, A. Because it has a lower mass, that means it has less inertia, which means it's easier to change its motion. Which is easiest to stop? A. Why? Same reason as above. Less mass, less inertia, easier to change the motion. If you took both trolleys to space, would they weight the same? Well, I'm going to call that a typo, because that doesn't even make sense. Let's just get rid of this T and say, would they weigh the same? All right, now if we're talking weigh the same, that's their mass, isn't it? So just because you teleported them to space, their mass wouldn't actually change. A would still have a lower mass than B. Now, whilst out in space, if you push both trolleys, would the need the same? Oh, this is a really Conglishy question. Would they need the same sized force to accelerate them equally? Well, no, they wouldn't, because the masses are different. Right? One's empty, one's full. Yeah, there might not be gravity around there. They might be described as being weightless, but they still have mass. And according to Newton's second law, when you have a mass, there we go, you need, for a bigger mass, if you want to get the same acceleration, you're going to need a bigger force. Right? I should probably just finish the equation there. So if you have a bigger mass and you want to accelerate them equally, you're going to need a bigger force. Okay, or if you had a smaller mass, you'll need a smaller force to get the same acceleration. There we go, Newton's second law of motion. All right, explain what is happening when the card is knocked quickly away from under the coin. Well, this is just like the hoop in the sugar cubes, isn't it? You're applying a force on the card, it gets flung out to the side. You did not apply a force on the coin, so it doesn't get flung out to the side, but it's no longer supported, so it will then drop into the cup, much like the sugar cubes dropped into the bottle. Okay, lucky last question now. We have two people on skateboards, one bigger than the other. If they push apart, which child moves the greatest distance? Straight up, this one. Now this is essentially just like the peg with the two marbles. All right. Now you might think, no, wait, the larger person is going to push with bigger force. No, but the people are pushing off against each other. So essentially, each one is going to be pushed with the same force. Now, according to Newton's second law, force equals mass times acceleration. So the bigger person is going to have a smaller acceleration. This will translate into not going as far. Okay, so just like the larger marble didn't go as far as the smaller marble, the bigger person won't roll as far as the smaller person. So there you go, Newton's second law of motion explains that. And that was the last question. We're done. So hopefully now you're pretty comfortable with Newton's laws of motion. Like the video, punch that like button. Want to see more videos? Smash that subscribe.